many students find questions difficult which are based entirely on diagrams. So, we will see a question which is based completely on diagram. Consider an ideal p-type substrate MOS capacitor whose charge distribution profile is also provided. The question for this diagram is, the p-type substrate MOS capacitor can exist in which region or regions if charge distribution profile is given. Options are depletion region, accumulation region, inversion region, and strong inversion region. Remember that it is a multiple select question, therefore more than one option can be right. Pause the video and try to answer the question within 60 seconds. The charge accumulated near the surface within the semiconductor is negative, so definitely it is not in accumulation region, as in accumulation region holes will be deposited for the case of p-type substrate MOS capacitor. Also, it is shown in the diagram that depletion width is smaller than the depletion width at threshold voltage. So, the strong inversion region is also not possible. Therefore, the possible regions for MOS capacitor is depletion and inversion region. Now suppose if there is a little change in the question such that it is also provided the surface potential is greater than Fermi potential. For this statement, two regions are possible, inversion and strong inversion region. For this data, two regions are possible, inversion and depletion region. So, the region which satisfies both the conditions is the inversion region. So, the answer will be inversion region. Now, tell me the answer if we had n-type substrate MOS capacitor in place of p-type substrate capacitor, then the answer would be accumulation region. These type of questions are preferred in competitive exams, particularly in GATE, where it does not matter how good you are in learning formulas, as you won't be using them in such questions. You are supposed to recall logic, facts, and characteristics of different regions and simply answer. Consider charge distribution profile for p-type MOS capacitor at flat band voltage. At flat band voltage, no charge is deposited anywhere. But if we apply gate voltage smaller than flat band voltage, then accumulation of majority charge carrier will take place. So, positive charge will be deposited near the interface within the semiconductor, whereas negative charge at the metal oxide interface. Similarly, if we apply gate voltage greater than flat band voltage, positive charge will get deposited at the metal oxide interface and negative charge will get deposited near the semiconductor oxide interface. As we keep increasing the gate voltage, the depletion width will keep increasing until it reaches its maximum value, which occurs at threshold voltage. In the shown profile, the depletion width is maximum, which occurs when the gate voltage is equal to threshold voltage. If the gate voltage is increased further, the depletion width remains nearly constant, but deposited charge increases. We represent the increase in charge in the form of a spike near the interface. This is a general charge distribution plot for a p-type MOS capacitor in strong inversion region. Once again, consider charge distribution profile at threshold voltage. From this concentration profile, we can get graph of electric field intensity with distance x. We got this profile by using the Poisson's equation. We have done the same analysis in p-n junction for finding different parameters like built-in potential and depletion width. For reference, the video link is provided at the top. You can check it. Similarly, from the graph of electric field, we can plot the graph of electrostatic potential. You can see the derivation in the provided links. Now, we will directly see the important formula which can be used in this unit. We can find the maximum electric field within the semiconductor to be equal to magnitude of charge on an electron multiplied by doping concentration into depletion width divided by permittivity of the semiconductor. Similarly, the electric field strength within the oxide will be equal to magnitude of charge on an electron multiplied by doping concentration into depletion width divided by permittivity of the oxide. From these two formulas of electric field, you can establish a very important relation, which is permittivity of the oxide multiplied by electric field strength within the oxide is equal to permittivity of the semiconductor into the electric field strength just within the semiconductor before the interface, which is also the maximum electric field strength within the semiconductor. This is actually a very important relation, as you can actually derive it from using concepts of electromagnetics. In electromagnetics, there is a chapter electrostatics. In that unit, there is a topic named boundary conditions, which have three cases. One of the case is when both the medias are dielectric. In this condition, normal component of electric flux density is equal within the two media, where the electric flux density is equal to permittivity of the medium multiplied by electric field intensity. Here, when we are dealing within a device, all the electric field component is normal only. There is no tangential component of electric field within the device. So, if we consider the first media to be oxide and the second media to be semiconductor, then the electric flux density within the oxide will be equal to electric flux density within the semiconductor just before the interface. So, the given relation can be derived from electromagnetics as well. Now we consider the graph of electric field and the electrostatic potential. We know that negative of integral of electric field with respect to distance x is equal to potential drop. If we have to find the potential drop that occurs within the semiconductor, then we will have to integrate this equation with limits of distance from 0 to depletion width and potential drop from surface potential to 0. So, to find the potential drop within the semiconductor, which is nothing but the surface potential, we have to integrate this equation. Also, on the left hand side of this equation, which is the integral of electric field with respect to distance x, this is nothing but the area under the electric field graph within the semiconductor. We will find the surface potential to be equal to 1 by 2 multiplied by magnitude of charge on an electron multiplied by doping concentration into square of depletion width divided by permittivity of the semiconductor. So, we found a formula for surface potential, but it may not be the case when all these parameters are provided and you have to simply put the values in the formula. Sometimes in the question, it is also possible that you are provided with the maximum electric field within the semiconductor and the depletion width, whereas the doping concentration is not provided. In such cases, rather than finding the doping concentration, you should simply modify this formula in terms of depletion width and the maximum electric field intensity. And by that, we will be having the formula for surface potential to be equal to 1 by 2 multiplied by depletion width into maximum electric field intensity within the semiconductor. The same way we can find the formula for potential drop across the oxide. The most important as well as the most basic formula is the total potential drop or the gate voltage is equal to potential drop across the oxide plus the potential drop within the semiconductor, which is the surface potential. It might be clear to you by now that we are having two parameters, one is Fermi potential and the other is surface potential. Fermi potential determines the strength of doping within the semiconductor, whereas surface potential determines the depth of potential drop that has occurred within the semiconductor. You should be using the formula for potential drop across the oxide and surface potential as per the data which is provided in the question. You should be quick enough to realize which equation you should be using to reduce the time and get the answer within least amount of time. But it is also possible that the question has provided you a completely different parameter. Like for example, in the question, charge per unit area is provided. Then in that case, we have to use another formula for potential drop across the oxide, which is charge per unit area divided by capacitance per unit area. This is not a new formula. We have used it in the previous lecture. It should be clear to you all that a parallel plate capacitor has two plates on which charge is deposited when a potential drop is applied across the plates. The charge on the two plates is equal in magnitude but opposite in sign. So, a little confusion may arise about what is this charge in this equation. In standard books, it is completely dependent upon the author, whether he want to consider the charge on the metallic plate or the charge on the semiconductor oxide interface. But here in my lectures, I will always consider the charge on the metal oxide interface. By using these values, we can get the gate voltage to be equal to charge per unit area on the metal oxide interface divided by capacitance per unit area plus 2 times of Fermi potential. As we know that at threshold voltage, surface potential is equal to 2 times of Fermi potential. This is actually the first time where we have considered the semiconductor has gate voltage equal to threshold voltage. Otherwise, all the above formula are actually valid for any voltage even if the gate voltage is not equal to threshold voltage. However, the formulas will need modifications if the MOS capacitor is in accumulation region. Whenever we study a device, we usually draw current voltage characteristic graph so that we can understand more about its behavior. But in case of MOS capacitor, generally there is no graph at all. This is because MOS capacitor is nothing but a capacitor. And since it is a capacitor, there will be no current at all. So the graph will be a single straight line which will be on the x-axis. A simple characteristic graph is shown representing 4 different regions of MOS capacitor, which are accumulation, depletion, inversion and strong inversion, and the most important voltage parameters, which are flat band voltage and threshold voltage. I will be using this graph in later lectures to make you understand some important points regarding non-ideal MOS capacitor. So keep this plot in your mind.